Hi students, today we're looking at volumes of a really specific type of cross-section. These are volumes that have circular cross-sections because they're being spun around some kind of an axis. So we're going to use a lot of what we just did in terms of cross-sectional volumes and try to make sense of that in a new way. Alright, so we've got this base of a region enclosed by these two things. We're just going to choose one of these things, and I'm going to say that this is going to be something that looks like this. The cross sections are isosceles right triangles with a leg in the plane. So that's like they're going this way. So this would be my side length, and that side length would be the top thing minus the bottom thing. So for the first piece of this, we're talking about the, and by the way, these are going to intersect at pi. So we're going from 0 to pi. And for the first thing, we've got area of a triangle is 1/2 base times height. Here the base and the height are both s, so 1/2 s squared. And in this case, s is going to be sine of x minus 2 sine of x. Well, it's actually minus negative 2 sine of x, so it's plus 2 sine of x. That would be 3 sine of x as a value. All right. For the second part, we're being asked to do the same thing, but if these triangles have their hypotenuse in there instead. So we talked about this, and if that were the hypotenuse, each of these would be that divided by the square root of 2 to get there. So our side lengths now are going to be that 3 sine x for going from top to the bottom, divide by the square root of 2. That means that my integral for this one is going to go from 0 to pi, 1/2 stuff squared, and it's going to be 3 sine x over the square root of 2. You could absolutely calculate these values on a calculator. I'm not going to worry about that. This was a nice review problem to connect to our previous stuff. Alright, so since we're talking about some revolutions today, we've got to start by thinking about what shapes would be formed if we spin these things around the x-axis. And the first one of these, if we think about this coming out of the screen and spinning down to this bottom piece, you might begin to notice that this is going to be a cylinder, that this line is spinning around and making that kind of hollow shape. For the second one, if we spin this around, we're going to get some kind of a cone structure. For the third one, I'm going to sketch that down there. We're going to get this weird kind of concave curve where we have this cone shape that kind of curves down to a point instead of is linear. And then finally, we have these two pieces together, and I'm just going to try to make that point. These are going to be terrible drawings, but we'd have this weird kind of spinny thing happening, and we'd end up getting what looks like almost a bowl shape, where the stuff that we'd be making the edges out of would come down to a point on the inside and look almost rounded, or would look rounded on the outside. So kind of a weird bowl that has a kind of tornado-y shape on the inside. So in terms of finding the volumes for these solids, we have some ways that we can do this geometrically without any calculus, but not for everything. So for that first one that we had on that screen, we know this is a cylinder, an excellently drawn cylinder if I do say so myself, and that my radius is going to be 3, my height is going to be 5, and if I think about cylinders, the volume is going to be pi times 3 squared. That's going to be my base, times 5. So 45 pi would be my answer for that. In terms of the calculus for this, what we're talking about is dealing with a integral from 0 to 5, and we're talking about this function that's built of circles. So let's call this pi times r squared dx, and in this case we've got y equals 3 as our function. So we're really thinking about this in terms of r squared is going to be just 3 squared, because the radius is 3 the whole time. So in this particular case, we've got pi times 3 squared dx. Alright, that's going to give me 9 pi x evaluated at 5 and 0. That's going to be 45 pi minus 0, which is the same thing we got using geometry. So that's kind of cool. We can do geometry or calculus and get the same answers. Alright, again, we've got a couple of different ways to do this one, because this is going to make a cone for us. And we know that cones have a volume that's 1/3 times the base area, which in this case pi r squared, times the height. In this case, we're just going to look at this with regards to our calculus. So here we've got a line that's y equals x. We're spinning it going from 0 to 3. We're spinning it around the x-axis. So we're going from 0 to 3. And the area formula for each of these things, again, are going to be circles. And my circles are all going to have a radius equal to x, because that's going from the x-axis up to that line. So I think it would be fair for us to write this as pi times, actually write this as x minus 0, because we're taking the height minus the x-axis, squared for each of those pieces, and adding up each of those circles from going from 0 to 3. And again, we're just going to do the setups for most of these. On the last one, I wanted to see that they came out the same, but this one I just kind of want to get the setup okay. And here's where we begin to have some issues. By the way, this is y equals x squared. This is not a shape that we have a volume formula for, so we only have calculus as a way to do this. But if we are spinning this around the x-axis, and we are going with a radius of that height, so r equals x squared, our volume formula, or area formula for our circles, is going to be pi times x squared. That's my radius squared, going from 0 to 2. We could also think about this spinning it around the y-axis instead. So here, I'm going to have to do this in terms of x instead of in terms of y. So if you have y equals x squared, if I wrote this in terms of y, that would be the square root of y is equal to x. And we're only dealing with the positive part of this, so that's totally fine as an equation. So that's going to be my radius going this way. And we're going from 0 to 4. So in terms of my y stuff, 0 to 4, square root of y dy, and I totally screwed that up because that should be pi that squared, and that's it. Looking at this one, what I'd like us to notice is that we're going to have kind of thinking about this as an outer circle and then cutting away an inner circle. So we're really dealing with this as kind of like a big radius going from that top function down to the bottom function. And then we're going to have a little radius going from the bottom function down to this axis of rotation. So in terms of what we're looking at, we're going from 0 to 1, and this is going to be pi big R squared minus, going from 0 to 1, pi little r squared. I forgot my dx's, those are important. So then our last trick is figuring out what our r values are. And I can't quite tell, but it looks like these are the functions. Let's call this square root of x and y equals x squared, because they look pretty symmetric. So I think that's a pretty reasonable guesstimate for those. They may not actually be those functions, but those are close enough for our purposes. Okay, so converting this, we're looking at 0 to 1 pi square root of x dx minus 0 to 1 pi x squared dx. Same thing's going to go on here. So we said that this was y equals the square root of x, therefore y squared equals x, and if this guy is y equals x squared, that's going to become x equals the square root. That's a terrible square root of y. We're still going from 0 to 1, but now we've got to think about this as the top one is the little radius, the bottom one is our big radius. So the integral from 0 to 1, and we said that the bottom one was the square root of y. So pi square roots of y squared, that's my pi r squared, dy, minus the small radius, 0 to 1, pi y squared dy. And that's it.